Hi everyone, thanks for tuning in to my Exam 2 example problems video. So I hope you guys all had a great spring break and that you're getting ready for this next exam. So before we get started, I would suggest that you go through and do these 26 problems first on your own, be able to see what material you're comfortable with, what you're not comfortable with, and then follow through with my video just to make sure that your answers are correct, and then you can skip to my explanations on questions that you maybe don't feel comfortable with. So again, to find those sample questions, go onto the Blackboard shell under course materials. Click on section 2 notes, chapters 7 through 11, and scroll down to the bottom to select the exam 2 example problems. So throughout this video, I'll be talking about the right answers, some general concepts that you should be familiar with the exam, and that kind of stuff. So to start off with question number 1. So under what circumstances will the distribution of sample means be normal? So again, make sure that you have a good grasp of distribution of sample means just as a general concept. So again, that definition is the set of means from all the possible random samples of a specific size n selected from a specific population. So when you're thinking about the distribution of sample means, you can basically think of it as a sample, but instead of using individual scores, it uses samples themselves and uses a collection of samples to make a conclusion about the true population. Because you're using actual samples, that's going to give you a more accurate idea of that population because you'll be using the means of multiple values instead of just single values. So when you're looking at whether or not it's normal, that question's talking about the central limit theorem, which again, if you're not very comfortable with, it can be found on the PowerPoint for chapter 7. But there are 2 points to the central limit theorem that this question really talks about. So you know that A is not the correct answer because the distribution of sample means isn't always normal. It often emulates the actual population, particularly if there's a small sample size, so you know that's not correct. But when you are looking at that definition, a distribution of sample means is guaranteed to be normal if either the population from which the samples are obtained is normal or if the sample size n equals 30 or more. So you know that B and C aren't the correct answer because while that can guarantee that a distribution of sample means is normal, it doesn't necessarily have to be one or the other. It can be either of those options, which makes D your correct answer if the population is normal or if the sample size is greater than 30. So number 2, sample size of n equals 9 are selected from a population with mu equals 80 or standard deviation equals 18. What is the mean or expected value for the distribution of sample means? So one thing that I really want to point out about this question is that you should know automatically when it says expected value, it is referring to the mean of the distribution of sample means. Those terms are interchangeable. You should know on the exam, if it just says expected value, make sure you know that that means mean. So when you're looking at this problem, it's kind of a trick question in the sense, again, because the mean of the distribution of sample means is the mu of the population, your answer is actually just going to be 80. So don't let the sample size or the standard deviation throw you off. If it says expected value, you're just going to want to pull from that mu. So number 3, if random samples each with n equals 4 scores are selected from a normal population with mu equals 80 and standard deviation equals 36, what is the standard error of the mean? So this is one of the formulas that you're going to have to know for the exam. So we're just going to pull out a blank sheet of paper and write that on out. So standard error, which is that sigma sub mean, equals the standard deviation over the square root of n. So in a problem like this, you're really just going to plug and chug. So again, in this case, for that standard error, this mu is really just meant to throw you off because it's not part of the formula, as you can see. So I would just cross that out right on your paper so that you know not to mess with it. But you're just going to plug in standard deviation equals 36. So 36 over and you have a sample size of 4, so over the square root of 4, so that's going to be 36 over 2 equals 18. So again, make sure you know that formula, and then you should just be able to plug in that number straight off the bat. So your answer will be C. One thing I want to quick touch on before we move on from this problem is to make sure that you know the difference between sampling error and standard error. So sampling error is the error between a sample statistic and the corresponding population parameter, whereas standard error, you can really just think of it as the standard deviation of the distribution of sample means. So make sure you know the difference between those two terms and that you don't confuse them. So for number 4, a sample is obtained from a population with mu equals 100 and standard deviation equals 20. Which of the following samples would produce the most extreme z-score? So right away, we're just going to write out that z-score formula. Again, this is one of the formulas you're going to need to know for your exam. So z equals m minus mu over the standard error. So again, if you want to rewrite this so that you really break down that standard error, I find that that helps me. So you could rewrite that as m minus mu over the standard deviation over square root of n. Means the same thing, because again, the standard error is the standard deviation over the square root of n. So when we are going back and looking at this problem, we want to find the most extreme z-score, and it's asking us about the difference between the sample size. So the sample could either be at 25 or 100, and then what the mean value is in comparison to that mu. So to get an extreme z-score, which again, z-score can be defined as the distance in standard deviations from the actual mean of the mu of the population, and we're gonna want a mean that's far away from that mu to get an extreme z-score. So when we're looking at the means, it could be 102 or 104. I'm just gonna automatically count out this A and B because you know that 104 is gonna get you a more extreme z-score than 102. So now when you're looking back at that sample size, so again, sample size is in the denominator of the standard error. So let's just pick an option and see where it goes. So let's say we did do this n equals 25. So in this case, that is a relatively small sample size. So let's say that we have a low sample size. That low sample size is going to increase your standard error because as you have a small denominator, the overall value increases. So you know that you'll have a high standard error. And when the standard error increases, you know that that's going to decrease your overall z-score. So therefore, you can conclude that having a small sample size will decrease your z-score, which makes sense because when you do have a low sample size, you can't be as confident with what the actual value is. So that will actually end up making your answer D because as you increase n, that increases the standard error, which overall decreases z. So if you get to this problem and that whole theoretical explanation kind of went over your head, that is not a problem at all. What I encourage you to do is just write out that formula again and literally just plug in those numbers. So you can come up with like a fake number for, well, actually it provides you with the standard deviation with the mu. So you can even say, like, let's say you're looking at number or option C, you can just say that 104 minus 100 over, and again, that standard deviation of 20 over the square root of 25, that is going to be your z-score for C. So if you just go through and do that for every answer option and calculate them, that's also another good way to find the most extreme z-score. So don't be worried if you're kind of struggling with that. So moving on to number 5, which combination of factors will produce the largest value for the standard error? So looking at this formula, again, standard deviation over square root of n. We want a large standard error. So if we want a large standard error, we are going to end up wanting a large standard deviation because if you know this formula and you know that increasing the numerator will increase the overall value, then you know that you want a high standard deviation. So looking back at this problem, we can automatically rule out C and D because you know you want that large standard deviation. So now when you're looking at the sample size, again, the sample size is in the denominator. So make sure that you really understand that when you decrease a denominator, that is going to increase the overall value. So that means that you're going to want a small sample size to correspond with a large standard error. So your answer is going to actually be B. And again, just like number 4, if you're really struggling with this, you get to the exam and you're not very confident, just assign values to these different options. So let's say you have a small sample, you're going to call small sample 6, and you're going to call a large sample 10, and a small standard deviation 1 and a large standard deviation 10. You can literally just go through and plug this in, and that's going to help you find the largest standard error. So just know that that's always a backup plan if you get to the exam and you're not really sure what to do. So as we move on to number 6, we're getting into material from chapter 8, hypothesis testing. So again, as a review, a hypothesis test is a statistical method that uses sample data to evaluate a hypothesis about a population. So we're using a sample to make predictions about the population. So number 6, what does a null hypothesis say about the treatment? So the difference between null hypothesis and alternative hypothesis is very important within psychology. You won't only need to know that for statistics, but pretty much every other psychology class you'll ever take. So make sure that you have a good grasp of that. So the null, just by definition, means that there's no change between your treatment, there's no effect, nothing changes, which is always just the initial hypothesis that we use because we want to prove that something actually is happening. Whereas the alternative hypothesis, which can be written as either HA or just H1, means that there was a change or a treatment or some sort of effect. So when you're looking at the answer choices, I automatically ruled out B and C because you know that the null hypothesis doesn't say anything about changing a score. You're not adding or multiplying anything. That really has nothing to do with null and alternative hypotheses. So now you're down to A and D. So A, the treatment causes a change. So again, when it determines that there is a change, that's when you're going to be looking at the alternative hypothesis, whereas no effect is going to be the null. So that answer is going to be D. So number 7, which of the following accurately describes the critical region in a hypothesis test? So a critical region, again, is where you set your point based on your alpha value for what is considered an extreme score. So when you're looking at these answer options, so let's say that this is our little distribution that we're using. And this, of course, is the critical region, this shaded area right here. And then in the middle, if you fail to reject, that's going to be dealing with the null hypothesis, which is that the null hypothesis is true if it falls outside of the critical region. So when you're looking at the critical region, the answer is actually going to end up being A, that outcomes with a low probability if the null hypothesis is true. So getting into this critical region is unlikely. The whole idea is that it's unlikely because that really proves that there truly was an effect. Because if you're saying if there truly is no effect, it's unlikely that we would determine that there is an effect, which is kind of the definition of that critical region. So you can rule out outcomes with a high probability because the high probability outcomes are going to land here in the null. And then when you're looking at option C, so this deals with whether or not the null hypothesis is true. Well, the null hypothesis matters because that's what we're looking at entirely. So you know that the option isn't, or the answer is not C because it does matter what the null hypothesis is. So overall, that answer is A, outcomes with a low probability if the null hypothesis is true. So now moving on to number 8. So what is a type 1 error? This is another one where you're just going to need to know these definitions for your exam. When I took statistics, I had a friend who kind of helped me figure this one out. So type 1, you're going to reject, which is one word, so type 1, one word. Type 2, you're going to fail to reject. So fail to reject is type 2. So that's an easy way to remember and be able to tell the difference is just by how many words there are. So when I was looking at this problem, I did notice that there was in fact a typo. So just keep that in mind. This option number C, instead of saying no, should say an effect. But so when you're looking at number A, or option number A, concluding that a treatment has an effect when it really does have an effect. So there's no error here because you said that there was a treatment, so you know the answer is not A. So B, concluding that a treatment has no effect, but it really has no effect. Again, there's no error there, so you know it's not B. So C, concluding that a treatment has no effect, but it really does have an effect. So concluding that a treatment has no effect, so again, that is failing to reject, but it really does have an effect, so you know that that's going to be your answer for type 1, which means that D is going to be, or type 2, excuse me, and then D is going to be your answer for type 1, concluding that a treatment has an effect, which means you reject, but it really has no effect. So when you see this kind of problem, which I'm almost 100% sure you'll have a problem that looks exactly like this on your exam, first just cross out the options that aren't in error, and then make sure that you know the difference between type 1 and type 2. Okay, so now number 9, a researcher selects a sample from a population with mu equals 80 and administers a treatment. If the researcher obtains a sample mean of m equals 88, which combination of factors is most likely to result in rejecting the null hypothesis? So when we're looking at rejecting the null hypothesis, we're gonna want an extreme z-score, which is kind of where my mind goes when I see this problem. So again, we're gonna look at this z formula. So it's asking us to look at the standard deviation and the sample size and how that affects whether it's rejected. So the standard deviation and sample size are the two parts of the standard error formula. So I'm just going to rewrite it down here so that we don't get confused with our last notes. So this problem is asking us for a likelihood of rejecting, which means we're going to want a high z-score. And to get a high z-score, we're going to want a low standard error. So we want a low standard error right here. So in order to get a low standard error, we're going to want this numerator to be low, because as the standard deviation decreases, the standard error decreases. And we're going to want a high sample size, because when you increase this sample size, your standard error decreases. So overall, we're going to want a high standard deviation and a low sample size. So looking at the standard deviations, to keep it low, we're looking at 5 versus 10. So you know C and D aren't the answer because you want that low standard deviation and that you want a high sample size. So that's that n equals 50, because 50 is greater than 25. So your answer is going to be B. Again, don't be afraid to plug and chug, just like those other problems that we talked about earlier. So number 10, a sample of participants are drawn from an untreated population with a mu equals 80. A researcher administers a treatment that is expected to increase the scores for the individuals and analyzes results using a one-tailed hypothesis test. So this is important. It's going to increase the scores. We're looking at a one-tailed test. So the null hypothesis would state that blank and the cutoff score for the critical region would be on the blank side of the distribution. So when I'm looking at this problem, I'm just going to draw a bell curve. Again, I feel like it really just helps visualize these kinds of problems. So I really encourage you all to draw bell curves when you have this kind of problem. So if you're expecting it to increase and it's a one-tailed test, we know that there's going to be a critical region on either side and not both. Because if there's a critical region on both sides, that's when you're dealing with a two-tailed test. So if you're expecting it to increase, chances are we're going to be putting our critical region on this right side, because what we want to see is an increase which will push the z or the t value over to this right edge. So when we're looking at the problem, we automatically know that the critical region will be on the right side. So let's cross out that A and C. So also when I see problems like this, I find it easier to write the alternative hypothesis first. So since we're expecting an increase, then again, we're gonna write mu, because we're making estimates about the population. So we expect it to increase. So we think mu is going to be greater than that 80. So that's the alternative hypothesis. So now what we're going to do is we're literally just going to flip this sign for the null hypothesis. So it's now going to be less than, and we're going to put the equal sign as well. Because if there's no change, so if mu is equal to 80, again, no change means that we're supporting the null hypothesis. So that answer is going to be mu is less than or equal to 80, which is option D. So the answer is D. So number 11, which of the following is not needed to compute a one sample chapter 9 t statistic? So when we're looking at that formula, again, make sure that you are familiar with t statistics versus z statistics. So again, t's aren't perfect when you don't know the population mean or standard deviation. That information just isn't necessary to conduct a t-test, which is actually the case for most real studies, because it's pretty rare that you know that information regarding a population. So when you're looking at the t formula, so you're going to be looking at the obtained difference over the standard error, which ends up being m minus mu over s of m. So which of the following is not needed to compute that t statistic? So m minus mu over s of m. So the null hypothesis value for the population mean, well, you need to know the population mean when you're computing a t statistic. You'll plug something in, so you know that's not true. The population standard deviation. So again, this actually isn't necessary. And the key word to this is population. You don't need to know the population standard deviation. If you do know it, then it would be easier to conduct a z-test. So chances are that's our answer. Let's just keep moving to make sure. So sample mean and sample standard deviation. Well, if you haven't conducted a sample, you can't conduct a test, no matter what kind of test it is. So we are just going to take out those answers, which makes 11B. All right, and then just a reminder too, when you're looking at this S of m, that will be your standard deviation over square root of n. Okay, so number 12, when n is small, less than 30, how does the shape of the t distribution compare to the normal distribution? So this is a pretty theoretical question. When we're going through the answer choices, so it is almost perfectly normal. Well, you know that's not true, because as your sample size increases, that's when you're going to get closer and closer to that true population, that true normal population. So that isn't going to be an answer. So it's flatter and more spread out, taller, narrower, or there's no consistent relationship. Well, as you remember in class, there is a relationship, because when you're looking at, so let's say this is the actual population. When you have less values in your sample size, you're going to be less likely of what the actual values are, which is going to end up making your distribution a lot wider and more spread out, which actually means that your answer there is B. But make sure that you're just really keeping in mind that that is because there's greater uncertainty. That's really the key to understanding this type of problem, because when you have that larger sample size, you are closer to your true population, which is when it becomes taller and narrower. So your answer for 12 is going to be C. So 13, a researcher selects a sample from a population with mu equals 30 and uses the sample to evaluate the effect of a treatment. After treatment, the sample has a mean of m equals 32 and a variance of 6. So which of the following definitely increase the likelihood of rejecting the null hypothesis? So when you are looking at this, you're going to want to look at that T formula. So again, that's right here, that T equals m minus mu over S of m, which can be rewritten as standard deviation over the square root of n. So we want to increase the likelihood of rejecting, which means we're going to want to have a high T value, because a high T value means that you're going to be more likely to push past that critical region. So what would increase the rejection? So answer A is increasing the number of individuals in the sample. Well, let's just test that one out. So if you increase n, that is going to decrease your standard error, right? And decreasing your standard error is going to increase your T statistic. So yes, increasing your sample size will increase your likelihood of rejecting, which again makes sense because we want larger samples because that will give us a more accurate idea of what is happening. So A is a possibility. So I'm just gonna put a little check mark right here. So answer number B is increasing the sample mean. So in this case, looking back at the problem, it says that mu is 30 and the mean is 32. So if you increase this sample mean, it's gonna end up putting a bigger gap between this mean difference, right? Because the mean is already higher than the mu, which means that it will in fact increase your t statistic because having a higher numerator will increase your overall value. But make sure that if you have a problem like this, you make sure that it's going in the right direction because like let's say that these numbers were flipped, then adding values to the mean would make that difference smaller. But in this case, it does widen the difference, which means that yes, B is also an option. So decreasing the sample variance is option C. So for option C, if you decrease the sample variance, that is going to increase the standard error, increase in the standard error. Excuse me. Decreasing, scratch that, decreasing the standard error or the standard deviation will decrease your standard error, and then decreasing your standard error will increase your t-value. Sorry about that confusion. So that actually is also an option. So then now option D, all the other options will increase the likelihood. So yes, we just proved that A through C will all increase the likelihood of rejecting that null hypothesis. So that is an option as well. So your answer is D. That's it. We'll just have to snip it. That's okay. We're gonna have to snip it anyways. All right, so moving on to number 14. So which of the following will not affect the size or range of a confidence interval? So again, make sure that you have a good grasp of confidence intervals. So that definition is a range of values that estimate the unknown population mean. So it will give us some sort of percentage. So for example, 95, you can say that you're 95% confident that the true population falls between, X and Y values. So when you're looking at this, what will affect the size or range of a confidence interval? First, we're gonna write that formula. So mu equals mean plus or minus the t cutoff, and then the standard error, that S of n. So when you're looking at the part that influences the size of the confidence interval is really what this question is asking. So first, we'll just go through the answer choices. So A, increase the percentage of confidence from 80% to 90%. So when you're looking at where that matters as far as the formula goes, you're gonna be able to find that in your T cutoff. So when you use your T table, it's gonna ask you what your confidence is as well as your degrees of freedom. So you know automatically that this is gonna influence the size or range because if you have a larger confidence, you're gonna have a more narrow confidence interval. So it's not A. B, reduce the sample size from 25 to 16. So again, that's gonna come into the T cutoff because it's gonna ask you for your degrees of freedom, which means that that also is going to affect the size or range of your interval. So C, increase the value of the sample mean. So mean is right here. So this I think is kind of a trick question because while the mean plays a part in the confidence interval formula, it isn't actually going to affect the range because it's just going to determine if it's higher or lower. So for example, let's say that this collectively ends up giving you a range of 5 values. Well, that 5 values, that width isn't going to change no matter where the middle point is. So that's kind of a trick question. So that actually is going to end up being your answer for what will not affect the size or range. So your answer is going to be C. So again, just make sure you know all the different parts of that formula. So number 15, which of the following is a correct way to report the results of a t-test? So when you are reporting a t-test, you always want to report the t-statistic and the p-value. So when you're looking at these, automatically I know C isn't correct because it does not report p-value. D is incorrect because you will never write out in a statistical format the words that P is significant. So that is incorrect. So now it just comes to whether or not degrees of freedom is reported when you're looking at the difference between A and B, and you are in fact supposed to report degrees of freedom. So make sure you're familiar with this format. So again, T parentheses degrees of freedom equals the value, and then P is greater than or less than whatever your alpha value is. And again, just know that you can also write P equals a value if you choose to. It doesn't necessarily mean that that is incorrect. So you could write, for example, like P equals 0.33. That also is an appropriate way to report P value. So as you're looking at number 16, which of the following studies would be most likely to use an independent samples design? So independent samples, again, is when you're testing for mean differences between two distinct populations. So for example, like students versus non-students, or testing between two treatment conditions. But the big importance when you're looking at independent samples in comparison to repeated measures is that you really need those two different groups. So again, we're looking for what would be most likely. So this first answer, examine the development of vocabulary in a group of children as they mature from age 2 to age 3. So again, this is repeated measures because you're going to use the same group of children twice. So it's not A. So B, long-term effectiveness of stop smoking treatment. So automatically, this long-term effectiveness really indicates that it's going to be the same person twice. So 2 months to 6 months. So it's not B. So C, compare the mathematics skills for 9th grade boys versus girls. So this is an appealing answer because it is just two separate groups that you're comparing. Let's just double check D to make sure that that's the correct answer. Compare the blood pressure readings before medication and after medication. Again, that's using the same group, so you know that's not right. So the answer is C. Compare the mathematics skills for boys versus girls in the 9th grade. All right, so number 17. One sample has n equals 10 scores and a variance of s squared equals 20. The second sample has n equals 15 scores with a variance of s squared equals 30. What can you conclude about the pooled variance for these two samples? So again, just make sure that you have a good understanding of that formula. So pooled variance is the SS1 plus SS2 over DF1 plus DF2. I believe that this is in the formulas that you are required to know for your exam, but you should still be comfortable using it. But it doesn't look like you're going to need to plug in actual values for this problem because it's really just asking you what the pooled variance will be relative to those two numbers. So because the degrees of freedom is the denominator, you know that sample size really plays effect. So when you have a larger sample size, that pooled variance is going to be pulled towards that number with the larger sample size. So in this case, that n equals 15 corresponds with a variance of 30. So because you have 15 people in comparison to 10, that pooled variance is going to be pulled towards that 30. So the answer will end up being B, that it will be closer to 30 than 20. So again, that variance will be closer to the larger sample. So number 18, an independent samples research study produces two sample means that were different by 6 points. The estimated standard error of difference was 2 points. So what is the value of that t statistic? So again, we are going to scroll all the way up and talking about the t, calculating t. So t equals m minus mu over the standard error. So again, just remember that that standard error is the standard deviation over the square root of n. So that's the formula that we're going to be working with. So in the problem, it lets you know that the difference between the two means were 6 points. So when we're plugging in the t value, we're going to know that the numerator is that 6, and then that the estimated standard error was 2 points. So we're going to plug in 2 into the denominator. So again, the difference in means over the standard error. So when you're looking at that t value, it's just going to be the 6 over 2, so your answer is 3. So just make sure that you're comfortable with that formula. Okay, so now moving on to number 19. So a researcher calculates an effect size through the standardized difference between two sample means and finds that Cohen's d equals 0.82. This is best described as A, so small, medium, large, or non-significant effect. So this one just comes down to making sure that you're familiar with those cutoffs. So the cutoffs again, so for a small Cohen's d is going to be a 0.2, medium is going to be 0.5, and large is going to be 0.8. So just make sure that you're familiar with those cutoffs. So again, since the Cohen's d was 0.82, you know that this is going to end up being a large effect. And again, just make sure that you know that Cohen's d is a form of effect size. Hop back onto the PowerPoint if you're not fully comfortable with effect size and its definition and its role in statistics. So number 20, what is stated by the homogeneity of variance assumption? So this one, again, is just dealing with definitions. I know that's really something that I've emphasized in this video, but what's more important, I would argue, than being able to calculate technical formulas on these exams is being able to understand all of those theoretical concepts. So this one's pretty straightforward. So again, when you're looking at the definition of the homogeneity of variance assumption, it requires that two populations from which the samples are obtained has equal variances. So two populations have equal variances is C. This, again, is just a matter of knowing the definition. So make sure that you're familiar with that. And then just in general, this assumption is necessary in order to justify pooling the two sample variances and using that pooled variance when you're calculating the t-statistic, which is why that's something that's important to know. So hopping down to number 21, which of the following is a correct null hypothesis for a repeated measures test? So again, to review, null hypothesis means that there is no treatment, no change, nothing like that. So when that's something important to remember. And then because you're making inferences about a population, when you're connecting these tests, you know automatically that your answer is going to contain mu and not mean, because mean, again, refers to a sample, while mu refers to a population. And what we're trying to figure out is information about the population. So you know it's not A and you know it's not D. So when you're looking at just the formal way how it's usually written in repeated measures, it is actually going to be this mu sub D equals 0. So then if it asks you for the alternative hypothesis, that will simply be mu sub D is not equal to 0. So it's exactly the same. You're just going to want to cross out that equals sign. All right. So now to number 22. So assume that this output you receive from SPSS of an independent samples test. So assuming that alpha equals 0.05, the variances for the two populations were likely, so either equal or not equal, and the null hypothesis for the independent samples test was rejected or not rejected. So when you're looking at testing for the equal variances, so right here, this test for equality of variances is where you want to be looking, and this significance is going to let you know whether or not equal variances were or were not assumed. So with this problem, if the significance is greater than 0.05, equal variances is assumed. But if the significance is less than 0.05, then the equal variance is not assumed. So make sure that you remember that for the test. So because in this example, the significance is 0.943, that is greater than 0.05, so you know that it was assumed, which means that the two population variances were likely equal. So C and D is not the correct answer. So now when you're looking at whether or not it was rejected, you're going to take this equal variances row and you're going to go all the way down to significance for two-tailed. So you've got 0.804. As you're familiar from everything else you've done in this test, if you have a significance that is greater than the alpha, so in this case 0.804 is greater than 0.05, then you are not going to reject, which makes your answer B. Okay, so number 23, for a repeated measure study comparing two treatment conditions, a researcher obtains a sample of n equals 9 different scores with a mean of 4 and a standard deviation of 6. What is the value of Cohen's d for these data? So Cohen's d, again, when you're looking at that formula, is just mean minus the mu over the standard deviation. So you're looking at the difference in scores over the standard deviation. So for this problem, it says that the mean difference is 4 and that the standard deviation is 6, which means when you bring that down, your answer is going to end up being 0.67. So your answer is C. Just make sure you're familiar with that formula and don't let this n throw you off. Make sure that you are using S instead of standard error, like lots of the other different types of problems for this exam. So number 24, if the variance in different scores was increased, what would the result be on the effect size of the hypothesis for a repeated measures test? So when you're looking at this problem, you're going to want to remember that the variance is in the denominator of that Cohen's d formula. So again, what we just wrote up here. So if you're going to increase your variance, as the problem is suggesting, so if you increase this variance, the entire Cohen's d value is going to be going down. So you know that Cohen's d, there is going to be an effect. So when you're looking here, both Cohen's d and likelihood of rejecting null hypothesis decreases, so that could be true. Cohen's d increases, we know that's false. There's a little no effect on Cohen's d, we know that's false because variance plays a part of that formula. And then same with d, isn't true. So just to make sure and make sure that the likelihood of rejecting the null hypothesis truly does decrease, what we're going to do now is that when you reject, because that difference in mean is over the variance, increase in the variance will decrease the likelihood of rejecting because you'll end up having a smaller value for that. So the answer is going to end up being A. So now for 25, compared to an independent measures design, a repeated measures study is more likely to find a significant effect because it reduces the amount of variance. So this is because it removes variance due to. So again, make sure you know the general differences between the independent measures and the repeated measures design studies. So the reason that it reduces the amount of variance, so again, independent measures looks at two different populations or two different groups, whereas repeated measures tests the same group of people twice. So it is going to end up being that individual differences that changes that variance. So all of these other terms are related to repeated measures, but don't let them fool you because, and then the effect treatment, obviously you're looking for an effect on the treatment in both of the different types of tests, which is why that answer is going to end up being individual differences. All right, so now we're moving on to our last problem, number 26. So a repeated measures t-test with n equals 25 participants produces a statistic of t equals 1.88. Assuming a one-tailed test with the critical region in the right-hand tail, what is the correct decision? So please pull up your t-table if you have not already. Just pause the video, get it pulled up so that you can follow along with me while we're talking through this answer. So, when we're dealing with this problem, I'm going to automatically just kind of draw a bell curve because that helps me be able to visualize some of these problems. I encourage you to do the same. So you know that the t statistic is positive. So we're going to draw the little critical region. Well, or not the critical region, but we know the critical region is going to end up being on this side because it is a one-tailed test. And then the critical region is in the right-hand tail. So we're trying to find where the cutoff is for this 1.88 depending on the alpha value. So when you pull up the table of critical t-scores, again, you're going to need that degrees of freedom as well as that alpha value. So in this case, since the n is 25, the degrees of freedom is going to be 24 because the degrees of freedom again is just n minus 1 which is that 24. So go down to the row that has degrees of freedom is 24. And then when you're looking at the alpha value, it looks like this problem's asking us about 0.05 and 0.025. Make sure that you're looking at the one-tailed values, not the two-tailed values. So make sure that you're looking at the correct column in that sense. So when you scroll all the way down, you're looking at degrees of freedom is 24. When alpha equals 0.05, the T cutoff region is 1.711. And when alpha is 0.025, then that T is 2.064. So when we're looking back at our bell curve, first let's look at 0.05. So in this case, your T value is ended up to be greater than the critical region. So because it's to the right of the critical region, you're going to reject. So we know that we are going to reject when alpha is 0.05. So now for 0.025, the T value is 2.064. So now the critical region is actually greater than our T value. So because it's greater than our T value, we are going to fail to reject, because it no longer lies in the critical region. So the answer then is that we are going to reject, so the researcher can reject the null with alpha equals 0.05, but not with alpha equals 0.025. So that is going to end up being our answer. You can just go through all the other options just to make sure that that is correct, but the answer ends up being A. So thank you for following along in this video. I hope it was helpful as you prepare for your exam over the next week. Feel free to shoot me an email if you have any questions about what I covered in this video or anything else that you've covered in class. Again, my email is lawre2ml@cmish.edu. You'll be able to find my information on the syllabus, so don't hesitate to reach out, and good luck on the exam next week. Bye.